5-number summary. All right. And what the 5-number summary is essentially the the 3 quartiles, Q1, the median or Q2, and Q3, and then the other 2 numbers are the smallest and the largest number. And then out of this procedure, we can do something to help us identify if something's an outlier, and we'll do that as well, because that 5-number summary is going to help us do that. All right, let me go ahead and put on my video here so y'all can see me up at the top up there. So here's just a little bit more of a visual of what the 5-number summary is. The minimum, the first quartile, the median, the third quartile, and the maximum. 3 of those are pretty easy to find. The minimum and the maximum, of course, are just the smallest number in the data set and the largest number in the data set. And then the median is the one in the middle. I know that's the thing we looked at the very start of this chapter. And then you can say the first quartile and the third quartile are equivalent to being the medians of the first half of the data and the median of the second half of the data, or the 25th and 75th percentile. And what I had shown you on doing that was the last thing we looked at, is you just multiply the number of pieces in the data set by 0.25, bump it up to the next whole number, and that is the position in your sorted data for the 25th percentile, and then you do the same thing for the 75th. Let's say, and then I had something here I was going to use. I was going to also show you, at the end of the day, I stayed a little bit late last time because of the fact that we lost some time at the beginning because of the audio. And what I had shown is how easy it really is to just put, well, let me back up a set. Once you have your data put into your TI calculator, you do one calculation and you get everything essentially in the chapter 3 in one kind of movement. So what I was going to show you too in Excel, how especially since some of the problems in your quizzes and homework, you can download it into a spreadsheet, and that way you don't have to worry about inputting the number on, because the input into the TI is the hardest part really, because when you're doing that, it's easy to skip a number and so forth. So you gotta double check and go about it. And I was just going to show you how the spreadsheet works too once we get to the end. I may even use it to do these things a lot quicker. But anyway, here's some data, and I've got that data here. I think, yeah, we did. This is the one we did. All right, close my darn thing. I closed my spreadsheet. I mean, my PowerPoint thing. But anyway, I'll just go ahead and shoot. Well, let's start back up. So this is that data that we have, and it's put into a spreadsheet. If it's not sorted, that data was already sorted, so I didn't have to worry about that. But if you put data in some other order, the way you sort it is to just click at the little, I think they call it a chevron in the column up at the top. You're not in the actual where the data's at, you're in the label, and you just put sort A to Z. And then that allows you really to see what the minimum, which is 0, and the maximum, which is 13.86, almost immediately. But let's see. So let's just put it here. Minimum is 0. So I'm just going to go through. 16.8, 13.68. We've already gotten these things. I'm just going to show you that you can do it with Excel. Let's see. Q2, which is the median. Now, in all spreadsheets and Excel and Google Sheets are really pretty much the same as far as the calculation. You can find the median by just putting an equal sign into the cell and typing in the word median. All right. Then you can go and then select all your data. All right. So 2.95. Now, at some point, they told us something strange here. Where are we at? I think we looked at this, but I also have that other class, so it's a little bit hard to remember, but I'm going to show you this again. And like I said, if you got any questions, just yelp, okay? Hold on a second. Maybe this, let me just double check and see if this is the same data. Because I'd uploaded PowerPoints like last week that were new ones that had a little bit more data in it. And this may be that old data. And if it says, yeah, this is that old data, it's 42. So, but I'm just going to show you how to do it, that it's easy. So they'll be different. So we're going to put here Q1, and there's actually a function called quartile. And you got to put in which one you want, and then you select all your data. So the reason why I did this in my other class with 42 is because I was kind of forced to use that older PowerPoint because of something strange that was happening with the PowerPoints. And another one, quartile. Oh, I see what it's done. I got it backwards. So you put in the data. And the quartile comes next. There we go. So you can get the 5-number summary like this, or with Excel. I'm sorry, this is like Excel, or you can do it with the calculator. But then once you got your 5 numbers, all this other stuff is easy. All right. So they went ahead and did it for us because they did it in the calculator, and like I showed you before when I stayed over last time, that's the hard part, is just putting the data in. But you're free to use the Excel or Google Sheets. All right. So here's the 5-number summary. The minimum and the maximum happen to be the same because of the fact that it's the same information. It was just 3 years added on. So the maximum was still the same. So look, once we have those things, and like I said, you can also do them with a calculator. And I wanted to show you could do it with Excel. But an outlier is a value that is considered that's considerably larger or smaller than most of the other values. And it's a good idea to be able to check these. Now, sometimes outliers are actually real values. And for example, with this rain, there was that value of 13.68, and it was heads and above everything else in the data set. But let me just kind of show you another example first. Here's some temperatures that were taken in some downtown city, and it was during the summer, and they took temperatures for 8 days. Now, they're giving them in Fahrenheit, and that's important. And we read them as 81.2, 85.6, 89.3, 91.0, 83.2, 8.45, 79.5, 87.8. Now, sometimes an outlier is just an error and probably could be easily be fixed. And we just, and especially if the data set is small, we might want to just see if there was a mistake in inputting it. And with this one, what do you think is different about this one value here, 8.45? Does that seem like a viable temperature for the summer, especially considering all of these other values in the 80s in the other part of the week? Well, obviously not, because of the fact that it looks like what this should be, and it was just a matter of typing in the decimal in the wrong place, 884.5. So this is an outlier, and generally what you'll do in this course for the through this book is, if something is identified as an outlier, you just take it and toss it out. In this case, we've just identified it as an outlier, but there's several different ways to approach that. You could just verify that it was 84.5 and fix it, or especially if you've got enough values, you can just take it out. Now, there's a procedure in this book for determining outliers, and we're going to go through that now. And this really be the kind of the heart of determining whether something is an outlier. And if something is an outlier, like I said, it can be one of two things. It can either be a value that is just kind of an error in input, or it can just be an extremely high value. And you just got to determine to make a choice about it. Now, the first thing we need for dealing with outliers is this thing called interquartile range. It's just abbreviated as IQR, which is simply the Q3 minus Q1. And notice that that is a positive number because the Q3 is always going to be higher than the Q1. So you're taking that difference between those two quartiles. It did it again. There's something weird going on. It looked like it was the expansion button, and it must be the X button. It's like something was missing on it. All right, let's get back down there. All right. I was trying to make it big like that. So this is a method that a lot of books use for detecting outliers. First of all, you find that IQR. And so once you get that number, you multiply it by 1.5 and then subtract it from Q1 and add it to Q3. All right. Now, that gives you a window sort of like this. And if you have any values on either side of those two of that window, it's considered an outlier. So here's some data, and it has to do with the number of students absent in a middle school in northwestern Montana for each day in January. And this would be the school days because, there's not 30 values or something like, let's see, what is it? 22 values. So that's just, Monday through Friday type days. So they use the calculator here in order to find out the Q1 and the Q3. And as I had said, when you use that calculator to do that thing, I gotta share it back again so y'all can see this. All right, so here's some data. So let's just go back since y'all, well, I think it closed before y'all saw this. But first of all, you just take the difference between Q3 and Q1, and then you multiply by 1.5, and then subtract that from Q1, add to Q3, and as I said, that gives you a window. Anything outside of that window, you're going to treat as an outlier. So here was some data, 22 values, and they pumped it into the calculator, and they came up with Q1 of 45 and Q3 of 59. And so that interquartile range, IQR, is 59 minus 45, so 14. All right. Now, taking that and multiplying it times 1.5 gives you, I'm going to do it on the calculator and just kind of report back to you just so I can. So 15 minus, 1.5. So that's 21 essentially. So 21 minus 45 is 24. And then also adding 21 to 59 gives you the 80. All right. So we're going to look at that data. If there's anything lower than 24, we're going to treat it as an outlier. That's all right, Don. I'll put you down here. I usually try to be flexible about this stuff, especially since, like I said, this is being recorded, so you can go back and. All right. So what we're going to do is go back and look at this data. And the first thing I'm going to look at is just, is there anything lower than 24 in there? 65, 67, 71, 57, 51, 49, 40, blah, 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 blah. There's nothing lower than 24. So there are no outliers on the lower side. But we can go through here and you can easily see that on one of these days, there was a 100. And remember, this is a number of school children absent. All right. So that one is definitely greater than 80. So this would be considered an outlier. Now, that does not mean it's not a valid piece of data. It's just that for this book, what you're treating it as an outlier. So if they tell you to take it out and do calculations without the outlier, then you want to do that. But 100 could be a viable value. It doesn't look like they meant to type in 10 because most of the values are in the 50s and 60s and 70s. So it's probably not meant to be 10. And what it could be is maybe there was some day that maybe that was a Friday and people were actually sick. There was something going around and that was just a lot more people out that day. So it is possible that it's a good piece of data, but as far as this is concerned, it's considered an outlier. All right, now you can use this 5-number summary to go ahead and build what's called a box plot. And a box plot is just a way sort of like some of the other graphs that we looked at, but it's a little bit more powerful. Remember, for a histogram, we can basically tell the shape of data by creating that histogram and just looking if it rises and gets a peak in the middle and comes back down at more or less the same rate. We can know that it's approximately symmetric. And the box plots can tell us the same thing. But the thing about the box plot is it tells us the most important things that we need to know, which is the Q1, the Q3, the median, and then the maximum and minimum value. Now, let's just kind of look at this. The middle value right there, in other words, that line in between the green and the red square, that would be the median. So for the 5-number summary, usually what you would write down there what the median is. The green line all the way to the left over here, that would be the Q1. And then all the way over to the right in that box, that would be Q3. So that's 3 of the numbers right there. This little line all the way to the left on they call it sometimes a whisker plot, box on whisker plot. Because of that line, they call it a whisker. But that little straight line there at the end would be the minimum value. Now, on the right side, you have something that's very similar, and that would be the maximum value that's not an outlier, all right? And what the red dots represent are values that were in the original data that were determined to be outliers. So we're going to go through this process, but that's what all these things mean. So let's go ahead and try to do this step by step. There's a nice little tool in Connect to do this. But we got the Q1 and the Q3 already. So the median is just a matter of copying off of here. So notice what they got down there in the bottom is like as a number line. So this thing is going to be true to, it's going to be proportional to what the values are. So they went by tens because you don't really need anything lower because there was nothing lower than the 40s and there was nothing higher than 100. And each one of the little tick marks at the bottom, as they've established, means 10. So what they do is they draw that vertical line right at 51 to represent the median. As I said, that's the median. On that left side, they go down to right smack dab in the middle between 40 and 50, and that's the 45. And then all the way over to the right, the Q3 is just a little bit less than 60 to represent the 59. Now, we've got to take care of those whiskers things because we need the minimum value, I believe was, they tell you on here it was 41. And then we already determined the maximum value was 100. All right. So now what they do is they can find those boundaries that we were talking about, the ones we just calculated. Oh, and I see you coming. Yeah, I'll put you on here. Did anybody else come in? Since I think I got it. Raina? I think I already got. No, I got you now. Sarah. All right. Brittany Bergeron, I don't see. And Amy. Oh, Amy, I see you. And then Tracy. I'm not sure if we've ever seen Tracy. I can't remember. Well, anyway. All right. So now, as we'd said, there were no outliers on the left. So you just basically, we'll see that second. But on the right side, and I'll just go back up and show you, that 77, since 100, we considered it an outlier. The largest one that was not an outlier, in other words, it was the first one less than 80. Because remember, 80 was, oops. So 80 was the lower boundary. I'm sorry, upper boundary. So that's why we're using 77, because it was the first one just lower than 80. And then we mark it right there. That's 77 right there at that end. 80 was the upper boundary. So 77 was the first piece of data that was less than that. All right. Now, they put an X over 100 because X was a piece of data. And like I said, it's also a piece of data that kind of, I wouldn't want to just say, well, we'll get rid of it because of the fact that it's an outlier. It may well be a valid piece of data, but we want the box to be represented truthfully, I guess you would say. So that's why we put an X there. All right. Almost done on this. You can even get the calculator once you got the data in there to do the box plot for you. How come they didn't do it on the other side? Oh, they did. So this right here on the left side was the 41 because that was the lowest piece of data. So right here was 45, and then this little piece right there would be distance of 4 down to 41, and this one is from what was it? It was 59, I believe it was. I'm surprised they didn't put the little vertical piece right there, but I guess they don't consider that important. So anyway, you can do them on here, and they'll do pretty much the same thing that we just did here manually. And if your box plot, is done correctly, you can kind of put it underneath that histogram and show more or less that it represents that same pattern in the data. So looking at this data here, they drew a little histogram for it as well. It goes up, it's got a peak, and it comes back down. Notice that the little box is tiny bit skewed. Now this isn't considered skewed because this data does have that peak in it. It wouldn't be considered skewed unless you didn't have the rise on that left side. So you can see that little bit of skewness in there. And then the X represents the the outlier. So on data that's heavily skewed, well, I guess they're considering it skewed right to a certain extent, but these are, and you can see the same thing that happens. I guess maybe that's not the same data. I just assume it was, but I don't guess it is. So kind of see how what happens is you got outliers on the right here that causes that skewness to the right. Outliers on the left causes it to be skewed to the left. And data that's more or less normally distributed, see, it's more or less everything, there's no outliers. And that's why it's important to either remove the outlier and do your calculations, or you can, or else it could well be skewed, or determine whether that should be a valid value and fix it. Now, these two things can be used to just determine normality, the histogram and the box plot. Now, one of the things that I like to bring up about judging normality, the closer the mean, if the mean, median, and mode are equal, now they'll never be perfectly equal, then that's another thing that you can use to determine normality. So I gotta figure that non-visual way, but all right, that's pretty much it for all that chapter 3 stuff. So if you got any questions, let me know. I'll be glad to go through if you got any questions from homework. Uh, perhaps. I mean, everything in statistics is usually just going to, it's like the standard deviation. I mean, you've got several steps in it, and you want to be able to kind of hit those highlights. Now, if you got something in specific, you know, of what you're talking about, most everything in statistics is kind of a multi-part answer. Now, as I said, I'd put this little review on here. Well, I don't know if you call it a review, a study guide, but I put it in the Canvas. And this is just the things that are important from the chapter to take out. Not from the chapter, the first 3 chapters. So it's important to know about the difference between a sample and population. Know about the difference between discrete and continuous data. Be able to tell whether data is skewed to the left, skewed to the right, or symmetric. If you're looking at a histogram or frequency distribution, be able to tell what the modal class is. The modal class, remember, is the one that's got the most in it. Now, the next 3, 5, 6, and 7, have to do with calculating, I'm sorry, 5, 6, 7, and 8, calculating the mean, median, mode, and standard deviation. Well, and it says on a large data set. Now, that means, when I say it means large, it's greater than 30, okay? Be able to calculate z-scores and put the, and, you know, be able to, let me back up. Be able to calculate a z-score given a piece of data and the mean and the standard deviation, and be able to put that in perspective of where it goes on the normal curve. Find the 5-number summary, find the upper and lower boundaries so you can determine outliers, identify an outlier, and determine what happens when it's removed. And then just know the difference between Chevy and empirical, and be able to use those. All right. So I was still got a little bit of time before I was going to take a break. But what I have to suggest, what I would suggest is, if you are able to work on homework or quizzes or anything like that, and have questions, consider this, and we'll do this also on Wednesday, work day, so that I can answer the questions you need. And, you know, remember, you can send me that help, ask my instructor thing, or you can just tell me where the problem's at, and I can bring up one. If I use one if you just tell me where it's at, like the number, then I can actually go through it and do the steps with you. It's hard to do that on those ones to show me, because they don't let me edit your problem. All right, so how are y'all doing with the homework? Last time y'all had a bunch of questions toward the end, because I want y'all to be able to get everything you got answered, okay? Okay. Well, like I said, I mean, that's what we're doing for a number of, I mean, we're not going to just do it right for a few minutes. We can do it for the rest of class, and then we'll also have a Wednesday to do this. But I want you to be able to get questions answered. And like I said, especially as related to these things, because these are kind of the important things that you see over and over, so to speak. Yeah. Well, stem and leaf. It's if you want to tell me which one, and I would can almost guess which one it is. Is it that back to back one? Yeah, of course. I mean, if I can find one. Because what you're doing there is, you one on the right hand side, it's normal, the normal way you would read left to right. On the left hand side, you got to do it like you were reading Hebrew, which is right to left, essentially. And let's see if I can find one for you. And then I'll draw it out. I think I'll be able to do it on the board. So hold on. So that's 2 point. I think that's 2.3. So there's one here. It's like with movies rated PG and movies rated R. Does that sound? Does that sound like what you're thinking about, Donna? There might be another one, but yeah. Okay. All right. Well, we'll throw that up here and we'll go through that, and that'll probably bring us up to break time. All right. All right. Let's see if I can project this for you, and then wrong one. They don't have. They both have the same name. The two, because I got two windows. It opens up two windows. All right, we're gonna play it a different way then. I already got the window, so I'm gonna close that one. I just want y'all to be able to see it. If I had another way I could copy it over, I would, but I haven't figured out a way to be able to dump an image in here. If I could do that. Okay, here we go. All right, so what we got here is we've got 12 movies top grossing in two different categories. We got on the left is the PG-13, and on the right is rated R. And just it's a good idea to read the instructions, even though when I do things like this, I usually try it first and then come back and read. But all right, so what we've got is the runtime for those movies. In other words, in minutes. So, for example, a 2-hour movie would be 120 minutes. Now it says construct a back-to-back stem plot for these data sets And if there aren't any values, leaves on a particular stem, then you're going to put the select the none button. Now, usually that just means putting an N in it. All right. Now, one of the things that will make this easier is to sort these. I'm going to download it in Excel and do that. You can do it by hand if you want to. You could also just go through them and do it in 2 steps by the way they did it in the PowerPoint or book, whereas you just kind of put them in the individual place that they go, and then in the second step you order them. But I'm going to kind of do it quick. So I'm going to order them off camera here. And I'm going to do the right first, since that's probably the easy one. All right. All right, so what I'm going to do is just use what they've got here. Now, on the R side, we've got an 88 as the first one. So I'm going to put an 8 there. There's a 3 here. There's a 4. There's a 7 and another 7. All right, see that? And you can kind of go back up here and look. See, you had 88, 93, 94, and 2 97s. Well, you don't have to. You're not, you can use the by hand. There's no problem with that. You're not at a disadvantage. I'm just trying to do it quick just to show you, because what they show you in that book is essentially how to do it by hand. Everything we go through via Bookwise, they show you how to do it by hand first, and then they show you that you can go ahead and do it with those things. But they've got those the ways to do it in there, especially when doing the calculator. But that's it. So if you do it by hand, then you don't want to learn those other things, then you can own that method. It'll work. You can do the whole standard deviation by hand. It just takes time to do it. So don't feel bad about it. It's just when you know another way to do it, like by doing it by hand, and you can do a calculator, you can check yourself on things. Now, like I said, doing it by hand is fine. You just got to own it, okay? Because one of the things that I find that students do in here, they see that they've got those instructions for the calculator and they think it's going to save time, and they'll do it, but they don't have any other way to do it to double check things. So doing it by hand is great. But I mean, you got to sort them some way. All right. So we put in 88 was the only one with an 8. The only one that began with an 8. There were 1, 2, 3, 4 that began with a 9. All right. Now, what was the next thing they said? All right. So next is 10. So just remember, that means right here, 93, 94, 97, 97. So anything that begins with a 10 And I don't believe there's anything that begins there with a 10. Do you see anything? No. So what we're going to do is say use the none button. All right. Now with 11, it looks like to me there are 4 of them. There's 110. I'm sorry. Yeah, 110, 118, 122, another a 111, and a 118. So we're just going to put them in the order that they give. I mean, I'm not going to. I'm going to sort them and put them in. But like I said, it's the way they did it in the book and in the PowerPoint is you can do it as 2 intermediate steps. Like just pick out the values and do it one time, and then the next time you can sort them because you can't do too much in your head. All right, so this would be 0, 1. Hold on a second. 8, 8, and I think that's it. It's 2 8s. So there was 11. I'm sorry, 110, 111, and 2 118s. So now that was the 11s. There were 4. Let's begin with 11s. 1, 2, 3, 4. But don't ever be jealous of people that use calculators. I mean, Amy, especially because I just have so many people, they'll get it thinking it's going to cure something for them, and then it really doesn't. I mean, and that goes all the way back to basic math. I mean, it really helps to be able to know that because if you make a mistake in putting something in, you got no way to check it. So it's always good to be able to do things by hand. So I always admire people that can do that. All right. So the next one is 12, and there's only one of those. And it was 122. There is nothing that begins with 13. There's nothing that begins with 14. There's only one that begins with 15 and one that begins with 16. So this is 15.7 and 16.5. All right. Now, this is where it helps to just be able to count because remember, if you've got 12 values in there, then you got them all, hopefully. So we got the 8 is 1. We got 4, that's 5. Another 4 is 19. Let's see. Hold on a second. Not 8. I'm sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Hold on a second. Did we get it right? It was 12, wasn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because I'm counting 13. If that's right, I need to go back and see. 93, 94, 97, 97. A none at 10. Yeah, that's right. So 1, so that's 5, 9. Hold on a second. I'm counting that as 2. So you're probably making the same kind of mistake too, but they got to be kind of. So that's 4 and 4 is 8, 9, 10, 11, 12. So we got them all. Boy, I'm going nuts here. All right. So what about the other ones? Now, here's where we got to watch out. We're going backwards. All right. So you're probably tempted to go the same direction, like do this and this. All right. Because up here, you got an 88 and an 89. But what's wrong with that? It's all right if that's a first step or an intermediate step, but you want to be able to go reading right to left. All right. So if you held it up against the mirror, it would look correct. There's two sevens. It doesn't matter about that order because there's two 97s. And there's also an 8. So we're going to put that first. So you can read them in order. 7, 7, 8. 97, 97, and 98. All right. There's only one here. See, it's the 108. Again, there's no. Yeah, there's two. There's 112 and 114 and 115. There's actually three of them. I was going to say that there's none, but it's 12. So it's 542. See that? So there's the 11, 12, the 11, 14, and the 11, 15. And then for 12, there's only one, 127. It looks like we're going to have a bunch of no's here in a bit. Is there anything with 14? Yeah, there's a 145, Lincoln. Whoops, there's no 13s. I'm sorry. So this is a none. And then the 145, only one of those. And then another none. And a 166. First one. All right, so you see how we got those? Yeah, like I said, it's on the right side, it just reads normal, lower to higher. But on the left side, it's backwards. It's a mirror. You need to have a mirror image. In other words, you're reading from left to right. I'm sorry, right to left. The opposite of way you would know. Now, that brings up well, okay, you can compare the distribution. One of the good things, besides that it actually encapsulates the data for you, is that you can see the shape of the data more sort of like a histogram. You can see here it starts off low, it gets high, has a dip with nothing in it, then comes back up. So that's what it's good for. It's like I said, the only benefit I see of it is just that it allows you to keep the original data, and if you got small data sets, you're able to do that. Whereas if you got lots and lots of data, you're not going to be able to use something like this. So it does have limitations. Now, one of the things I was going to mention, I bet you another one that you had questions about. Let's see if I can find it. See, and this one is just kind of having you go backwards. In other words, 140, 140, 141, 145, 153, 157. 164, 167, 169, 169. There's nothing that begins with the 170 and then 18, 180. But I was going to show, because there's another one in here I thought about. Well, there's another one like this. I thought there was one in there that had I guess that maybe they took that one out. So instead they got two of these comics. There was one in here, and I guess they took it out, but it was one where you had to pay attention because they wanted you to do to break the 14s into two, like anything 140 to 144 and anything 145 to 149, but they don't have that one in here anymore. Probably just as well. But the good thing about it is you actually get to see the data, and you get to see it ordered, and you'll be able to see the shape of it. Like I said, it's got limited value because you can't really do that with a whole lot of, real big ones. All right. Any other questions about? Let's see. Did y'all have any trouble with the histograms? What intervals are you talking about? Well, I mean, that right there is a class width of 2, because there's two whole numbers in there, 3.0 and 4.0. And like I said, that's a class width of 2. Because your next one, I'm sorry, it's the next one. So the next one would begin with 5.0, and then go out to 6.9. And then next one starts at 7.0 and goes out to 8.9. But that's what they call class width of 2 right there. You got two whole numbers in there. But those are what called classes. That would be like a first class, or they'll give you that one and say have a class width of 2, and they'll give you that first one, and then you just keep adding 2 to both the 3 and the 4.9, and that'll give you all of them, and you keep doing that until you pass up your largest piece of data. Yeah, either any two successive lower limits or any two upper limits. But like I said, that's probably the easiest way to think about it. But like I said, if you look at that one right there, 3.0 to 4.9, there's actually two whole numbers in there. Everything from 3 all the way up to the very end of 4. But most people, when they count, they wouldn't start counting at 3.0. So that's why they show you to just the difference between any two successive classes. Well, actually, it's 6.9, 5 to 6.9. See, because if you're adding 2 to 3.0, yeah, you get 5.0, but 2 to 4.9 gives you 6.9. So that's the way you determine all the rest of the classes. It's just adding your class width all the way down, and you keep going until you get to past your largest piece of data. All right. So, like I said, I would really like to see y'all working on stuff and give me questions, because we'll take a break in a little bit, and then y'all can just bring any questions you got, and I'll be glad to go over them. Like I said, I put that little study guide. It's the important things out of the first 3 chapters that you really want to be able to take out of all this, because those are the important things. You'll need them for that first test. And then you'll see them probably still popping up after that, like I said, throughout the whole course and for the exam. I mean, they include the stem and leaf, but I don't think it's that hugely important as the histogram. Yeah, 5 to 6.9. Like I said, if you had a class with the 2, then the next one would be 7 to 8.9, 9 to 10. What is it? 9 to 10.9, and so forth. And you just keep going to wherever your largest piece of data is. I was just yeah, I'd be glad to do that. All right. As a matter of fact, I think in this thing we got something. All right. So remember, for the most common type of data that we're looking at in this class, and then when we get to chapter 6, what happened to the picture? Oh, yeah, it was just there. Now it's gone away. We can see it in the preview. All right. I'm going to open it back up because I mean, I like to show these pictures if I can. But what the empirical rule essentially is, it applies only to what's called, what they've told you so far is called approximately symmetric. Another word for it is bell-shaped. And the more formal term is normally distributed data. And when we get to chapter 6, we're going to work exclusively with that type of data. All right. So if we have data like that, then we can use the empirical rule to do that, because if we know that it's approximately symmetric, and considering I probably went through this pretty quick last time because of time constraints, now's a good time to go over it again. Well, I just don't get what's going on. I'll just have to get another one for us and pop it in the notes. So now in real life, there's no data that's perfectly symmetric, or there's very, very few of it. So we just need to know that it's approximately normally symmetric. All right. And I was trying to find one that looked similar to the one they were showing us, because this is something you kind of gotta latch onto the coattails of the book for, because of the fact that they're establishing, the trend of what looks normally symmetric. Hmm. All right, so let me pop this into the notes and then I'll show that. I said I don't know why the videos aren't displaying. I mean, the images aren't displaying in those PowerPoints. All right. All right, so if we got data that's approximately symmetric, then they'll tell us that. In some cases, they'll have us look at a histogram, or even you can do it with a box plot. And like I said, also, if you look at the relationship of the mean, median, and mode, if they're really like close to one another in value. But I was trying to find one that looked kind of real. Let that one pop up. Again, everything's kind of moving slow. But again, this one's not perfect. It's a little bit more perfect than I would like it to be, because the one in the book is a little bit less perfect, but yet they determine that it's normally distributed. And like I said, it's really smart to be able to look at it from different vantage points. And that's why you use a histogram and a box plot. And you can do that, what I'd said about mean, median, and mode as well. But if we've got data that's approximately normally symmetric, in other words, we know that it's shaped like that, then we can do certain things with it. Now, obviously, if we know that it's normally distributed, then we can use the empirical rule. Let me pump that back up for you. All right, so here we go. The curve on here looks perfect, okay? But that's just so we can show that no matter what the thing looks like, as long as it's determined that it's approximately symmetric, then we can know these three things about the data. We can know that within one standard deviation on either side of the mean, in other words, whatever the mean is, if we add one standard deviation and subtract one standard deviation, then that gives us about 68% of what's underneath that curve. And that's why they say approximately, all right? Because remember, nothing is going to be exactly perfectly symmetric like the one that they're showing you in there. Just thought of something. Let's see if this happens if I try to paste this in my notes. All right, I thought I could copy it. But it was just there a minute ago, and now it's gone. But anyway, so That's what the empirical rule is about. So if we want to find the boundaries of 68% of the data, then whatever our mean is, we're going to add to it 2 standard deviations. Now, this was data that we looked at. We did a stem and leaf plot on this. This was 51 values, and it was the percentage of people 65 and older in all of the states plus District of Columbia. Now, again, I don't know why all of a sudden this thing is deciding not to display that image, but they just show you one that looks more or less normally distributed, and they're calling the shots on it and saying this one is normally distributed. So now, what does that mean? Well, if we know, and we, because also on this little thing, they gave us the mean and standard deviation. This right here that's not displaying, right? It was the TI 84 plus printout of all the things that we needed. It's that one thing that I showed you at the end of the class where you type in the data, you hit the 1 var sats, and you get everything. And then they'd also done the histogram for it. So they said on there that the mean was 13.249 and the standard deviation was 1.6827. All right. So if we subtract the standard deviation from that mean, then we get that lower boundary for the 68%. That's 1 standard deviation down in the negative direction. All right. And then adding 1 standard deviation to that mean gives us 14.93. So back to this. So for this particular data that we've got, so this was the 11 point, what was it? 11.57 is right here, and 14.93. So 68%. Yeah, these are the page numbers. 61 is where the empirical rule is at. And I went through here last week, and I redid all these and uploaded them to make sure. Like I said, I don't know why all of a sudden now this stopped displaying. I never had that do that. Because somebody in my other class said that they were having something funny happen with them too, and I went and make sure. So this is the 11 point number, and that's the 14 point number. So those are the 2 endpoints for 68%. Likewise, if we want the boundary of 95%, so they tell us there's a 68%. So if we want to do 2 standard deviations, 2 times 1.6827 minus 13.24 gives us 9.88, a little bit less than 10. And in here, we add that same number to the, this is 13. Plus, and we get 16.61. So basically from 10 to 17, depending on how accurate we want to be, is the boundaries of the 95% of the data underneath there. And as I had showed, if you go through and look at all this data, there's hardly any, there's only 2 values less than 10. There was 8.1 and 9. So that's 2 values that were less than 9.88. And there's only 1 value larger than 16.61, and that was the Florida value, which was 17.78. So that's 3 values out of 51 that are outside of the 95%. And as I remember, if you do the calculation, if you do 48, which is 51 minus those three, 48 over 51 is 94%. So it's almost right on there. It was 94 and some change, not quite 95. And then if you go 3 standard deviations, so 3 times 1.6827 is just a little bit more than 5. So subtracting 5.0481 from 13.29 gives you 8.2. And then adding the 5.0481 gives you 18.3. There was nothing higher than 18.3. There was only one value lower than 18.2. It was the 8.1, which was Alaska. So 50 out of 51 are within or almost all. And you can do that calculation. I think it was 98%. So that's how accurate these can be, even though, we just know that it's approximately that value. It's not going to be 100% necessarily all the time, and maybe some of the times it won't be, but all right. Well, I tell you what. Well, let me just break and then we'll do a break. Now, because all of these over here look fine. I don't know why it's just that one little section. All right. Now, they give us, when we start talking about Chebyshev, and they call it an inequality, and there's a reason for that. It's because they're going to use this term called at least. They're not going to say approximately. They're going to say at least, because that's usually what inequalities do. At most or at least. You're not looking for equality. You're looking for a range of numbers that are at least a value or at most a value. And so what they show you here, instead of that nice and neat, approximately symmetric thing, what they show you is they show you just any old data set, and they have to make one up because this could apply in 2 cases. If you don't know if the data is normally distributed, so in other words, you don't know, there's no mention of it, or if it's not, then you're forced to use Chebyshev. And what you're going to give up in the use of Chebyshev is just accuracy. You're going to be less sure. So they just show you a data set. It doesn't have to look like this, because there are all kinds of data sets they could show you the histograms of, and they're not going to be approximately symmetric. This is just one example. So if we don't know the distribution of it, or if it's not normally distributed, then we're forced to use Chebyshev. Now, this is the formula that you kind of use for any number of standard deviations. K would be any number of standard deviations. If you were to use 1, it really doesn't make any sense to use 1, but it's not going to be 68%. It's going to be a lot lower. It's not even going to make sense to you that. So the first one that's going to make any sense is 2 and 3. And usually those are the only 2 you'll ever look at in this course, is the 2 and the 3. Do you understand why from K equal 2 and K equal 3, it's 75 and 89%? I can show you over here if you want to see it. Well, that's what K, yeah. But you understand what happens is when you square K and it's in the denominator, 2 is going to be, yeah. I mean, like I said, the only reason why this would be important is if you want to do it for another type of standard deviation. But generally, the only ones you're looking at are those 2, so that's why they give them to you. So 1 minus So 1 over k squared. So let's just set k equal to 2. So 2 squared is 4. 1 from 4 is 3. Keep the same denominator. So that's the 75%. So if k is equal to 3, it's 1 over 3 squared is 1/9. So that's 8/9. 1 from 9 is 8. Keep the same denominator. And that's approximately equal to 89%. If you take 3 and divide by 4, you get 0.75. And as a percentage, it's 75%. 8 divided by 9 is 0.89999, something like that, or 0.88888, which rounds off to 89%. So that's where those come from. So, but the heart of what Chevy is just that well, when you say it's a little bit easier, but as I said, it's really not as much use as the other one. All right. So all this is just saying they're just showing you how 2 standard deviations and 3 standard deviations shake out. So remember, with 2 standard deviations on the empirical rule, you know that it's 95% approximately. But all Chevy is going to give you is just this, and this is the key word: at least 75% is within 2 standard deviations of the mean. Not as accurate, because that's 20% different, actually, going from 95 to 75. And on 3 standard deviations, remember that was the almost all? Well, 89% is the trade-off. And like I said, I don't think I've ever seen in this class anything other than 2 and 3 standard deviations. I mean, if you wanted to, you could do the 4, 5, 6, and 7, and 8, but I seriously doubt you're going to see those. I know you're not. All right, so let's take a break. Come back with your questions. If you want to be working on your homework and you got things that you want to share along the way and get help with, please do that, because it really makes time go by faster if you got questions and that I can help you with. Of that, at the high point, right at the hinge point of where it's a mirror image. All right, so that means in the one little chunk to the right, you've got approximately 34%, and then on the other side to the left, 1 standard deviation, you got another 34%. So that's that whole red area is 68%. All right. So 1 standard deviation, what that essentially means, what a standard deviation really means is, for normally distributed data, you've approximately got 3 standard deviations that make up almost all that data. So it's just a question of, if your standard deviation is a big number, that means that is a very fat hop you're taking. And each one of those 2 red hops to the left and the red hop to the right are bigger depending on the size of the standard deviation. And if it's a smaller number, it means it's a smaller hop. But every one of these normal curves, no matter what it is, it's approximately 3 standard deviations make up almost everything that's underneath there. So, like I said, as I was trying to think if I could show you and give you some credit for that term wiggle room, because that is something that we look at when we start doing like confidence intervals or margins of error, that's essentially more what that is. Because margin of error is sort of like wiggle room, but that's really not what this is as far as I can see. All right, so and what I had found too. So when you're talking about though with the Chevy, then we all we can say is that we've got at least this much in between those number of standard deviations. And remember, K could be 2, 3, 4, 5, and 6, but generally you're only looking at 2 or 3. So they just show you another example of a curve that's not normally distributed. This one is skewed to the right. And that's what Chebyshev just tells you, that you got at least, for if K is equal to 2, you got at least 75% of the curve underneath in that red area. And if you go out to K is equal to 3, it's very close to 90, 89%. All right. So what about question-wise? Anything else I want to know about, or is that not clear enough? Because I'll be glad to find something else. There's all different kind. Like I said, there's different books, and they show you different ways of kind of talking about it. But generally speaking, you're talking about data that you know that's normally distributed, and that way you can be fairly accurate with the approximately the 68, the 95, and the 99.7, or you have to jump to at least when you're talking about not knowing its distribution. So, and let me just kind of tell you this. So, if you're looking at a problem and it's and you see this term, uh, yeah, and then like I said, is if you know that if there's some, and that's something generally you have to be told unless you can see it for yourself, unless you got the histogram for it and you can call the shots on it. But generally speaking, you're going to be told that it's normally distributed. If you're not told that, that's one hint that you got to use Chebyshev, and you know it's not going to be as accurate. And then the other thing is this term at least, because that's the phrasing of Chebyshev. So we can go back to that one that I showed you. It says at least. So that right there, at least. So that's how you know it deals with Chebyshev. And then just kind of, you got that formula, or you can just kind of remember 90s, what is it, 75 and 89. Either way. But the process of finding out how many, if you're told at least how much data is in between these two values, well, if it's two standard deviations, you would use 75. If it was 3 standard deviations, you go to 89. Let's see. Oh, you know what? I think there was a problem in there that we probably could have looked at. Let's see. Yeah, there was. Now this one just flat out tells you to use Chevy-Chev, but all right. So this one just tells us, as part of a public health study, systolic blood pressure was measured for a large group of people. The mean was 120 and the standard deviation was 10. Now, they don't mention anything about it being normally distributed, but they do say, what information does Chevy-Chev's inequality provide about these? Well, the two cases that we really looked at was 2 and 3 standard deviations, because those are the most common, okay? So 2 times 10 is 20. 20 from 120 is 100. So that's the lower boundary. And then adding 2 times 10, which is 20, to 120 is 140. So at least 75% of people tested will have that blood pressure between 100 and 140. And if we want to know the 3 standard deviations, well, you got to multiply that standard deviation by 10. I'm sorry, but the standard deviation of 10 by 3, which gives you 30. So it goes down to 90 as the lower end, and add 30 to 150. So it goes to 150. So at least 89% had systolic blood pressures between 90 and 150. So at least, see that key word. Whereas in the empirical rule, the key word is approximately. Approximately. And of course, you know that it's normally distributed. Whereas with Chevy-Chevs, you don't know anything about it, essentially, or you know it's not normally distributed. All right, anybody come up with anything else? Y'all need to start coming up with these on your own, or else we'll have to make y'all do stuff. I figure y'all got enough to do with that homework, because that covers the main points, plus it's got a lot of little other things in there that the department likes. So I'm saying, if you're able to work right now and get on there and get stuck on something, you can feel free to send me your questions. Like I said, I can come up with something for you to do, but it's much better to have to do the homework, because it's all the same kind of things. Let's see if I can find something here for y'all. Okay. Well, just shoot if you got a question. Like I said, I know this stuff's coming due this week. like I said, we got the rest of the day, and we got Wednesday, like I said, to handle any kind of review. Uh, I was trying to find one, but they some of these they use terminology and stuff. I think it'll just make it worse. I'm gonna just bring up the textbook and look from there. Well, I mean, they don't so much create skewing, but the median is not. Remember, it doesn't get affected by a large value or small value. So what happens, because the mean is sensitive to those extreme values, um, skewness, the side that the data is skewed to, is what side the mean gets pulled to. The extreme values pull the mean in that direction. So if remember on the example with where the person won the lottery, that extreme value, it pulled the mean in the positive or the right direction to the right in the upper side. Whereas, yeah, another way of saying it is the mean is sensitive to extreme values. I like that term a little bit better, but it means this is the same thing. They're opposites of one another, but yeah, the mean isn't resistant to the outliers, whereas the median is, because the median doesn't take into account whether the values on the end are really extremely low or extremely high. So as we showed on that example where we compared them, the mean for before the person won the lottery, the mean was like I think it was $28,000, something like that, and then the median was pretty close to being the same thing. And then after they won the $1 million, well, the mean shoots up by $200,000 because you're taking that $1 million and chopping it into 5 pieces. So that's why it gets added 200,000. So it was 238,000, I believe. Whereas the median, it just jumped up by 10,000 because that was because of the shift in that one value, but it doesn't take into account that the extreme values, because it's not looking at the extreme values in the calculation of the median. All right, let's see. All right, here's something I found in the book. See if I can paste it in. All right, so you got a certain type of bolt used in an aircraft must have a length between 122 and 128 millimeters in order to be acceptable. The manufacturing process produces bolts whose mean length is 125 millimeters with a standard deviation of 1 millimeter. So we've gotten the two important things we need there, the mean and the standard deviation of 1. All right. So 2 standard deviations. And that's what that means, 2 SDs. All right, so there's 2 standard deviations. It's just simply 2. Now, let's look at the endpoints. All right, so that's 125 minus 2, 125 plus 2. So that's 123 to 127. All right, so this is two SDs. Now, we're still inside of that, so let's go one more. All right, so here's the endpoints. And this procedure is the same thing that you're doing when you're using the empirical rule. It's just that the percentage is different for 2 and 3. And like I said, is for non-approximately symmetric, and this mentions nothing about it being approximately symmetric, then we got to revert to Chebyshev. So this one is the 75. And then this one is the 89%. All right, so what are they? It's 125 minus 3 and 125 plus 3. And we got this one that keeps the math simple. So that's 122 and 128. All right, so we did everything we really can do here. So the end point for 89% is 122 to 128. So you'll notice that back up in this problem, those are the numbers that they mention. So here's just a question. Can we be sure that more than 85% of the bolts are acceptable? Can we be sure of more than 85%? Yeah, because is this greater than 85%? And it surely is. You're getting more than 85% acceptance. And really, the reason that we know that we're fooling with Chebyshev here is because there's no mention of normal distribution. So we're going to just be less accurate than if we knew that it was normally distributed and we could go to empirical rule. Well, sure. but it's not going to change anything except the percentage now. So you've got to be able to know those percentages, and you know how to get them. All right, you got to have some kind of way. Like I said, I wish I could drop an image in there, but I'm just going to have to do this. All right, so we got everything we kind of know or need to know there. Yeah, so you got to have just some way to remember those things. I mean, in truth, on that formula sheet, I mean, it's on there. Like I said, you just kind of got to kind of know what that relates, that's what it's for. All right, so a data set has a mean of 20 and a standard deviation of 3. A histogram shows that the data is approximately symmetric. Is it appropriate to use the empirical rule to approximate the proportion of data between 14 and 26? All right. Yeah, because they mentioned that it's normally distributed. They could show you a histogram or something like that, but since I can't paste one in there, because I actually gave one on this problem that I found. So yeah, we can use it because we know that it's normally distributed. So now we're just going to do those calculations. So let's find out. So the mean and S was equal to 3. So what I'm going to do is I'm going to do one at a time. So this would be one standard deviation. So X bar 20 minus 3 and 20 plus 3. So we got 17 and 23. This is 2. And this is just number of standard deviations. All right, so now we got 2 times 3 is equal to 6. The standard deviation is 3. So then that's 20 minus 6. All right, and so this was right here. Remember, this is one standard deviation, so this is 68%. One standard deviation. And so here it's going to be 17 and 26. I'm sorry. It's 14 and 26. And see, there's the numbers that they mentioned. So this is 95%. So that's the approximation. So a 95% is within 14 and 26 because 14 is 2 standard deviations below, 26 is for 2 standard deviations above. I mean, if you wanted to do almost all, you could do that too, but they didn't do it. But if you did 3, It's 3 times 3 would be 9. What in the world did I do? I did it backwards. 3. So then it's 20 minus 9, which is 21. And then 20 plus 9, which is 29. So this is almost all. Like I said, when you get into chapter 6, they'll start using the 9. It's 99.7. And this is why I was saying is knowing the size of the standard deviation. If it's a small number, that means your data is all. Oops, I got to put my camera back on so y'all can see me doing these hand motions. So if the data is real skinny, which would be like if you had a standard deviation of 2 or something like that, like this one had a standard deviation of 3, then that means that the standard deviations are real small, so you got a real skinny curve. And then if you got a huge standard deviation, that means it's fat. Because in all cases, you're going to have 3 standard deviations that make up almost all of the data, almost that whole curve. Just chopping it into 3 pieces. It's just how big of pieces they are. Because the bigger they are, the larger that number is going to be. But there's always going to be 3 underneath there to make up almost all of it. Well, yeah, they all, I was trying to find, it's hard finding a good one. I want to find good visuals because I can't draw stuff like that. Try another time to find something good. Here's something. It's not a histogram, but it kind of give you the idea. Because usually when you're making the judgment, you're not really doing it based upon an actual curve like this. You're basing it upon a histogram or a box plot or something like that. But this just kind of shows you that all 3 of these are normally distributed or approximately symmetric. It's just that you can have ones that are skinny and ones that are fat and ones that are in between. And the empirical rule will always apply in either of those cases because it's still, you still got 100% underneath there, 50% on either side because it's symmetric. And so all these things will still apply. That one standard deviation, even for that red one, even though it's got a real small standard deviation, there's still just 3 standard deviations on either side of the mean that make up almost all of that data. Same thing with the big fat one. No matter how skinny or fat the distribution, there are still 3, All right. So, like I said, did y'all see that little thing? I mean, since I don't want to. Did y'all are you able to find that? It's in. I put the link to it up at the top, but I said there's like 12 or 15 things here, and I'll try to do that for each one. But these are the key things that are important. I mean, in chapter 1, I mean, you're just talking about the difference between sample and population. Discrete and continuous data is the most important things to take out of that. Yeah, I'll be glad to do that. I mean, I'm always going to post everything. It just still take a little bit of time because, um, especially on this class, it takes all of them take. The larger you make the video, I know it takes 2 days to put it on there, but you'll be able to see it. And then, like I said, what I've also been doing is after the Tuesday class, I picked the best one of those 2 days, and I'll post it on YouTube as well, and put the link in there. Of course, now that you know where they're at, even if I don't put the link, you can probably find it if you want it. But as long as as it records, it's going to be there in the conferences. That's just kind of automatic if you tell it to record it. It just takes a couple of hours. Well, good. We just need to kind of get a rhythm going here, Different students like different things, so. Yeah, it's just that's where it always shows up. And remember, like I said, it stays for 2 days. I mean, 2 weeks. But what I've been doing is putting on YouTube. So that way, if you need to come back to it later. Well, stick around if you got questions. I don't want to make you stay up, but I don't mind staying up a little bit. I like it when y'all ask questions because, like I said, I just can drone on about most anything. I just like to know what to drone on about. Well, if I go to sleep, I'm gonna take an actual sleep. I don't know. Friday I went. It was the first day, after the week. I had a really nice bike ride all the way out to almost Venetian Isles, and then I went and did a whole bunch of other stuff, cut grass, everything. And then Saturday I couldn't move, and I thought it was just had to overwork myself, but I think I have like a cold or something. So I zonked out on NyQuil last night, but I feel a lot better now. Hopefully I'm just on the mend now. Because generally I don't like taking naps, even though, especially at night, I can take naps. But then I'll wake up and then I'll stay up till all hours. So